Good morning, good afternoon, or good evening. This is going to be a full paper work through of the recent November assessment set for Year 13. Ideally to show off not only the correct answers, the correct ideas, but hopefully also the thought processes that go into both solving the questions you're used to, but also the questions that maybe you've never seen before or haven't practiced as much, or that are just a bit different. So we'll jump straight in. So we always have our multiple choice questions to start. We're looking for the range of values for which this is valid. Now in the formula booklet under the expansion, it does tell you this is valid for mod x is less than 1, or particularly that bit is less than that bit. So for this one, that's saying that the mod of x over 4 is less than 1. Multiply it by the 4, this is mod x is less than 4. Question 2. We have a sum to infinity of a geometric sequence of -3. Every term is multiplied by -2. What's the sum to infinity of the new sequence? Well, with negatives, it can be a little awkward to think about. But if you imagine the sequence and you just double every single term and add them all up, well then your final answer will be doubled. But we're going by -2, so we're simply multiplying every term by -2, so therefore the sum to infinity has to also be multiplied by -2. Question 3. This one is the first one which has a notation you probably not used or seen before. If you take a moment to think what that's saying, we're looking for the y values that are stuck between the quadratic, that's my quadratic, and that's my straight line. So that is one way to describe the region shaded grey. If we want the area of that, well, if we were doing it manually, we would integrate between the limits of the line, and then we'd subtract off the integral between the limits of the curve. And one really nice property of integrals is if the limits are the same, the dx's are the same, you can just subtract the curves underneath the integral sign. So really this is the integral between 5 and 0 of the line, subtract the curve. And if you expand that carefully with the negative signs, you end up with that solution there. Notice that the first one is almost exactly this first line here, but without the limits. So they've tried to give you the hint that that is the correct idea by having that one answer not quite being correct, but being a very, I wouldn't say it's too subtle, but it's a relatively subtle hint. Okay, if we move on to now the long answer questions. So question 4, we must show detailed reasoning. That's just a cheat they have so that you don't sketch it in your calculator and use your calculator function modes to just write down the stationary points. We actually need to show it. We want to show it has no stationary points. Well, as soon as we see stationary points, we need to be thinking dy by dx. If we differentiate this, bring down the power, reduce the powers by 1. Now, for a stationary point, we need this dy by dx to be equal to 0, namely 3x squared minus 6x plus 4 equals 0. But the question is trying to say that we have none. So really, this equation shouldn't have any solutions. Well, it's a quadratic, so that means we can start using the discriminant. So I'm going to consider b squared minus 4ac. I'm going to show that I'm calculating that times 3 times 4. And if I put that into my calculator, that comes out as -12, which is less than 0. So let's write down our conclusion. Therefore, well, we've actually shown that this thing has no roots, which therefore would imply that the curve has no stationary points, because that was what that equation was describing. And notice with solutions like this, particularly with show that questions, just putting those odd little words, those odd little connectives, really elevates your solution. It keeps yourself focused, but also makes it much easier for the examiner. So just the little things like, I know what I'm planning to do. I'm telling the examiner what I'm planning to do. Adding in these little connectives between the lines to show the flow of logic that you are using. Question B. Show it has exactly one point of inflection. Well, it has no stationary points, but you can have inflections without stationary points. If you remember, the definition for a point of inflection was the second derivative, and it's not just equals 0. The second derivative changes sign. So we need the second derivative, and we need to show that it changes sign through its solution, not just there is a solution. So we already have dy by dx higher up, so we need to differentiate that again. So it's going to be 6x minus 6. I was looking at the line up here for that. And then, well, if you change sign, you have to go through 0. So this is when x equals 1. And there's lots of ways to justify the change of sign. You could sub in 0.9, see what you get. Sub in 1.1, see what you get. I like to just look at the shape of the thing. And as d squared by dx squared is linear, there's no x squares, it's just an x and a number, it changes sign through its root. So again, it's a show that, I need some kind of conclusion. Therefore, we have exactly one root, sorry, not root, the context is inflection, exactly one inflection at x equals 1. A relatively simple question there. Just remember, making sure that you remember the facts about stationary points and inflections. Question 5. We have a strange context here. We've got James saving money to buy a printer. He saves a different amount every week, and it's even told you, it's said exactly the context you should be thinking. We're in an arithmetic sequence. It takes n weeks to save £64, and we want to show that equation. Okay, well, if we set it up, this is an arithmetic progression with first term, well, in week 1, he saved £10. The common difference, we're saving 80 pence less, or £0.8 less every single week. And we want the sum to equal 64. So I'm going to use my SN formula, which I'm going to quote for the examiner first, and put in what I know. I know I want my sum to be 64. Now I don't know the n, so I'm going to leave that as just n. I know A, and I know D. Notice I put the D in front of the bracket this time. That's just our normal way of writing our algebra. Now we need to simplify. I don't like having a half, so I'm going to double everything. And then I'm going to start simplifying inside the bracket. I believe that's going to come out as 20.8. So I've got a 0.8 times the 1 minus 0.8n. And I'm doing this in a lot of detail. I'm not skipping any steps because it is a show that question. So I'm trying to keep it as obvious that I'm not cheating as possible. Now, because of the structure of the question, I know I'm just going to have an n squared at the end. The last bit of non-special rearrangement is to move it all to the same side. And now I'm actually going to divide by 0.8. The answer seems to imply that that gives me a nice number, so I'm going to believe it, and I'm going to check it in my calculator. Now notice I have written the divide by 0.8 on the side, so the examiner knows I haven't just fudged the final line. I do actually understand how I've got from the penultimate to that final line. If you don't write that thing there, it can look like you've just written the top answer because you don't know how to proceed. Okay, nice little bit of algebra for that show that. We now need to solve this equation. So if I want to solve this, I've got my calculator, I can solve with that mode, or I could factorize. This one turns out to factorize incredibly nicely. So I get answers of 10 and 16. Hence, state the number of weeks it takes James to save enough money to buy the printer. Well, this is a quadratic function. It has two answers. He's going to have saved already at n equals 10. So it's going to take him 10 weeks. A brief reason after, and we could work out exactly how long after a number of weeks, he will start saving negative amounts. If you started saving £10 a week and you save 80 pence less every single week, eventually you'll start saving negative. So 16 weeks is kind of, I'm thinking of this as a graph, he's saving more and more and more, and then eventually he starts saving negative. So if we want to be at this 64 level, that was at 10 weeks. Here we've gone up and then we've gone back down again. So 16 weeks is after saving negative amounts and coming back down to the 64. Now it's only a 1 marker, so the brief reason does only need to be brief. I'm not 100% convinced that I've written that in the best possible way, but as long as you pick out the right value and you give some reasoning about why you chose the 10 and not the 16, you should be okay. That's question 5 done. Question 6, and they're starting to use these questions more and more, where here are some methods, critique them. So we've got our two characters who have integrated 1 plus x squared using different methods. Amaya's just increased power divided by the new power, but Ben expanded out first. Now it appears that their answers are different because Amaya has a third, whereas Ben does not. And that's what Charlie has noticed. Do I agree with Charlie? No, I don't agree with Charlie. Both are correct. And this is quite a subtle thing with this plus C. Both are correct, but have different values of their plus C. These two answers are identical up to a constant, and that plus C is absorbing any constants already. So no, I don't. Both are correct. They have different values of plus C, which absorbs the third. Again, only 1 mark. We don't need to go into glorious detail there. Part B. We're given that a is a constant bit greater than 1. Find that integral, giving your answer as a single fraction in terms of the constant a. Now, if we look back to part 1 of the question, it kind of gives us a hint of how to do this. If we write this up as a negative power, we can use Ameyer's method, increase power divided by the new power, to do this very simply. So increase the power to -1, divide by the new power, divide by -1 between a and 1. Sub in the values, that's going to be -1 over a plus 1 minus -1/2. It wants it as a single fraction, so we've still got to do a little bit more work. I'm going to deal with all the brackets first. My common denominator is going to be 2 lots of a plus 1. So there'll be an a plus 1 on the first, subtract 2, or a minus 1 over 2a plus 1. Again, just some careful algebra being applied there. Next part. We're given the area between 1 and a is equal to 1/3. Well, that's exactly what we've done in part B. We found the area between a and 1. So that a minus 1 over 2a plus 1 is, the area is that 1/3. Find a. Nicest way to deal with a fraction equals a fraction is to multiply up by the denominators. Multiplying up by 3 is going to put a 3 on the left hand side. Multiplying up by 2a plus 1 puts that on the other side, and both fractions have cancelled out. Now it's just a linear equation to solve, which leaves me with a equals 5. And at this point, it would be really smart in your calculator to evaluate the integral between 1 and 5 of 1 over 1 plus x squared dx using your calculator's special abilities. If you type that integral in, unfortunately I don't have my graphical calculator with me, you should get 1/3, and you can be then very happy that you've done probably both part A and part BI and part BII correctly. Final part of the question, part C. Find the exact value of that. Now there's actually many techniques for questions like this. You could do a substitution. That will work. Turns out there's a really nice trick for this one, and that's by observing that the numerator looks very similar to the derivative of the denominator. So this looks very much like f dashed of x over f of x, and that integrates to ln plus c. So we basically have that set up, except here my f of x is the sine 2x. If I differentiate that, I should expect 2 cos 2x, but I don't have the 2. So I'm going to put it in, but to put it in I need to correct by it. So I'm also going to put a half out in front. And now this simply integrates to a half ln sine 2x plus 2 between those limits. And now we sub our limits in. Sine of pi by 6 is one of our exact answers. So it's either a half or √3 over 2. Of course, you would check it in your calculator, even if you are confident. It comes out as a half. So when I sub my pi by 12 in, I've got a half plus 2. So that's 5 over 2 minus a half ln. When I put 0 into sine, I get 0 half ln 2. So that's going to be a half ln. Subtracting logs, you divide 5 by 4. And again, although the question said find the exact value and we had to do it this way without cheating, use your calculator at the end. at the end, type that integral into your calculator, type a half ln 5 over 4 into your calculator. If they give basically the same answer, you know you've got your answer correct. Lots of these little exam technique checking styles, which mean both you can be confident you've got it right so you can move on quicker, and to highlight that you have actually made a mistake rather than just staring at it for ages, wondering if there's a mistake or not. Question 7. We have another show that question. This time we've got quite an unpleasant fraction and we want to differentiate it. So I'm going to use the quotient rule. I'm going to write this as u over v. So dy by dx is going to be u dash v minus u v dash. That v did not look good. U v dash over v squared. So my u was 5x squared plus 10x. This is now just going through the process. V we've put as x plus 1. So v dash, bring down the power, reduce the power by 1. Officially we'll also times by the derivative of the bracket, but that's just 1. So there's no extra adjustment there. Now we need to put it in. Our u dash is 10. And I'm actually going to do something a bit weird. I want to write this as 10 brackets x plus 1. Because if I'm looking at the answer, I'm seeing these x plus 1s everywhere. Chances are something will cancel. So I'm actually going to pre-factorize. So that's my u dash times v, x plus 1 squared, minus u. I could factorize that one, but I don't see anything that will end up cancelling nicely. So I'm going to leave that one unfactorized, times by v dash over v squared, which was x plus 1 squared. This is now to the power of 4. And yes, one of these do indeed cancel. I've got an x plus 1, and one of those x plus 1s. Now notice if you are cancelling, you have to cancel it out of every single separate term. Notice I did not cancel it out of this part because this was attached to the other x plus 1. I've got an x plus 1 out of the way from there, whereas over here, well, I had to take an x plus 1 out because it's a separate term. So, well, it's claiming that a and n both have to be constant, so my numerator has to turn into just a number somehow. So I'm going to expand out my numerator and hope magical things end up happening. I have a square bracket minus 2 lots of, and I can do 2 lots of that. I'm being extra careful with my brackets for now. I'm subtracting 2 lots of, so I put a big subtract in front over the x plus 1 cubed. And now let's simplify. I've got 10x squared minus 10x squared, they cancel. I've got 20x minus 20x, they cancel. So I'm left with 10 over the x plus 1 cubed. A is then 10, n is then 3, and I'm done. And actually on reflection now, noticing that factorization didn't help, because I could have cancelled one of the x plus 1s out of this section, I still would have had to do exactly the same process. Sometimes tricks like that are super important and super helpful. Here, it was not. Okay, part B. Hence, deduce the values of x for which the derivative is negative. So I'm trying to solve 10 over x plus 1 cubed is negative. Well, if a fraction is negative, either the numerator is negative or the denominator is negative, not both. So that means that we have to have this denominator being negative. A cube is negative only if the original is negative. So this is when x is less than -1. And if you did try and do this any other way, if you did try and multiply up by x plus 1 cubed, well, that'll be times it by 0. That cancels out. That's not a good time. So you do have to use a little bit of the logic there instead. Question 8. A paragraph of text. An artist is creating a design for a painting. It includes a set of stairs of varying heights. In the painting, the lowest step is 20 and the height of each other step is 5% less. Quite important to notice that our steps are getting smaller. If in the painting the total height is 205, how many steps? So this is quite a difficult one to determine what topic it is. So let's do a bit of exploration first. The first had a height of 20. The next step is 5% less than that. Well, to find 5% less, we times by 0.95. So my next is 19. And I can times by 0.95 again, 1805. And we can keep going. Well, this is starting to look like a sequence. And if you were acknowledging what I was doing in each step, I was multiplying by something. So this feels now very much like a GP, a geometric progression. Our first term is 20, and our common ratio, what we multiply by each time, is 0.95. And we've been told that the sum of some number of steps is 205. Well, now we know everything except for n, so we can set up an equation. Our Sn equation, a 1 minus r to the n over 1 minus r, that's going to be 205 equals 20, 1 minus 0.95 to the n over 1 minus 0.95. Well, that denominator is 0.05, so I'm going to multiply up by 0.05. I'm also going to divide by 20 at the same time. So it's going to give 0.5125 is the 1 minus. Move the power and the 0.5 thing to opposite sides. It's 0.4875. Just making sure as I'm doing this I'm not making any unfortunate errors. So I'm just double checking a couple of my calculations because these numbers do look a little bit awkward. Now if I want the n, normally the best way is to take logs. If you've got a power equation and you want the power, taking logs is normally the most efficient way to do it. Now it does not matter if you took ln or log, every single one gives the same answer quite conveniently. And if I've typed all of that in, my calculator pauses for a moment to do the calculation, and it gives me something awfully close to 14. So I'm just going to quote 14 as my answer. There are 14 steps. Linking back to the context of the question is always a good idea. Okay. Difficult question to get started on, but as soon as you notice it's a GP, a very common style of question. Question 9. The equation of a curve is, well, here we've got our x and y's all mixed up. We want to do something with the gradient, so I'm now having to think about implicit differentiation. It's not just y equals, so we need to use our implicit techniques. First thing I'm going to do is actually expand out that bracket. I could differentiate it with that bracket. That just feels a little bit too difficult and is going to mind meld me just a bit too much. So I'm going to simplify my life by expanding out that bracket. and then I'm going to diff. So differentiating, if you differentiate an x thing, you do it normally. If you differentiate a y thing, I'm going to do this actually in a really odd order. I'm going to jump to the other side. If you differentiate a y thing, you need to put a dy by dx next to it. So 4y would differentiate to 4. Because it was a y, a dy by dx pops in. The 2x just becomes a 2. The 8 disappears. The y squared would differentiate to 2y, but it was a y thing, so I put a dy next to it. And then finally, the 2xy is the most difficult term. We have to product rule that. So I could do the 2x multiplied by the derivative of y plus the y times the derivative of the 2x. Do that term slower if you need to. And we have this nonsense. We want the dy by dx, we want in the gradient, so I'm going to rearrange this. I'm going to factor, I'm going to bring all the dy's onto the same side, factor out all of that stuff, so I've moved that 4 dy by dx onto the left. And on the other side, I'm going to put all the terms without. So my dy by dx is the horrible fraction as so. I've actually got a common factor of 2, which I could divide through by, but that seems like extra effort. Now, I haven't actually really read the question yet. I've just seen the word gradient, and I've just ran with differentiating. So let's see what the question needs. The curve is intersecting the positive x-axis at P. And we want the gradient at P. The thing about implicit is you need both the x and y components, coordinates, to find the derivative. So if we intersect the positive x-axis at P, that's telling me that my y is 0. So at y equals 0, let's try and solve the original. So that'll be x squared equals 2x plus 8. Make it equal to 0. Use your calculator or factorize. So we have our solutions as negative 2 and 4, but we were told it intersected the positive x-axis. So we're going to reject the negative 2 and say P is 4, 0. So now we have our coordinates, we can go back to the derivative. Dy by dx, therefore, is going to be equal to 2 minus 2 times 4 minus 0 over plus 0 minus 4. So that's negative 6 over 4 is negative 3 over 2. Well, the question was to show that question and wanted 3 over 2. So at this point, we should be pausing and being very, very carefully checking through our work. It looks like we have a sign error. So big things to check is, have I done this rearrangement correctly? Did I accidentally move some negative signs in the wrong place? Appears to be fine. Did I sub in correctly? Appears to be fine. So here you'd spend a moment. It looks like we've done something wrong. You can check those key places very carefully. But if you spent a minute or two and you can't spot an error, there are two things that you should probably do. One, I've forgotten the two things. I had two things. First one, move on. Come back to it later. You've checked your technique. You've checked your working. If you have made a mistake somewhere, because you've checked everything, chances are you'll only lose a mark or two at the end. Your method is correct. So one, move on. Two, if you do really trust yourself, the other one, which I was thinking, fudge it. Put your final answer as a positive 3 over 2. You might get away with it. You'll lose the same number of marks either way. If they spot where your error is and they notice that you fudged it, they will give you the same marks as before. And it actually turns out with this question, it was unfortunately a typo of the question itself. The question itself should have been negative 3 over 2, which was just an error in writing the paper, unfortunately. But in either situation, either moving yourself on or sneakily changing to make your answer fit, you'll get the same number of marks if you don't spot the error. And in this case, you would get all the marks with negative 3 over 2, because that's what it's supposed to be. Part B of the question then, find the equation of the normal to the curve giving your answer in that form. Now luckily part B does not require part A, so actually using the positive 3 over 2 or the negative 3 over 2, we will give you full marks for using either of them in this part B. In that form, so we're going to be using our equation of a line, so y minus y1 equals the gradient x minus x1. I've used the coordinate 4, 0 because we're going through P. Now the question wants it in the form with everything being integers, so I'm going to double the equation and I'm going to simplify out the other side. It wants x and y on the same side, so I'm going to oblige, and there's my final answer. Question 10. A binomial expansion. Find the first three terms. In the formula book, your expansion always looks like 1 plus x. And that's exceptionally important. You have to have these expansions as 1 plus. It does not work with anything else. So I need to get that 4 out of the way. So I'm going to factorize out that 4. If I factorize it out, I need to be able to put x over 4. But when that 4 comes out of the bracket, the power of the bracket still impacts it. So it's really 4 to the negative a half as it comes out. So we factored out the 4, but we need to acknowledge the fact that that power still has a say. And you can do 4 to the negative a half in your calculator, or just realize it's 1 over the square root of. And now I'm going to start doing my binomial expansion. As with most of these questions, it is only the first 3 terms. The first term being being nx, negative a half, negative x over 4, plus your next term is n minus 1 over 2, x squared. And here ensure that you've acknowledged that we're not using x. If we compare that thing with what's actually in my bracket, that x is negative x over 4, and we need to write it as a negative x over 4 every single time. And now it's a simplification. We have, that's going to be a positive 8th x. That one's just a little bit more complicated. Is it 3 over 32? Again, use your calculators carefully there. And finally put the half back in. That's 3 over 64 now, x squared. I like to always have this plus dot 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 on the end, because officially it is, there are more stuff going on, so we do need to acknowledge there is more. You don't get marked up or down for it. The expansion of this thing is 16 minus x. Oh, this thing looks very similar to the first part. If I write the denominator up with a negative power, we've already expanded that 4 minus x to the negative a half. So this is a plus bx multiplied by a half plus the 16th x plus 3 over 64 x squared, etc. So let's see how we would create the the constant and the linear terms? Well, the only way to make the constant is from the half a, the front, times the front. So a half a equals 16, so a must be 32. The only way to make the x term is from the half times the b, or the a times the next term up. Nothing with the x squared is going to come into play. So that's plus a 16th a is going to equal -1. Well, that's just another equation to solve. That's going to be 2. So a half b is -3, b is -6. It's worth just making sure that the algebra didn't go terribly wrong at any point, and that looks okay to me. Okay, quite a common question that they like to do an expansion, work out some missing stuff in a separate expansion. Question 11. Again, we've got this bold nonsense at the top. That is preventing you from either sketching or putting that into your solver mode, finding x and then putting tan x and see if that was root 3 root 3 or not. So we need to not avoid entirely, but avoid a little bit our calculator. Now what this question is, that the key point of this question is we just have tan of x, whereas both of these have nonsense x in there. We've got a combination. So the first thing that we should be doing is trying to expand that nonsense combination out to make it just x. And that means using our addition formula. Now they are given to you. Sine of a plus b is sine a, cos b, plus sine b, cos a, and the other one, cos a plus b. The coses go together, so that's cos minus sine. Actually, because these are subtractions, we can even pre-subtract. So that'll be a subtract, that'll be a plus, that'll be a subtract, and that'll be a plus. So let's apply it in our case. So you've got two lots of sine x cos 60 plus, and because I've got two lots, I'm going to put a 2 here as well, sine 60 cos x equals, well, for the cos it's cos plus sine. Now 30 and 60 are particularly nice ones. You can do it in your calculator to make sure you get the right ones, but they're the half or the root 3 over 2. So cos 60 is a half, so that first term is just sine x. Sine 60 is root 3 over 2, so that's just going to be root 3 equals cos 30 is just root x, so root 3. Root 3 over 2. I was getting a little bit worried because I thought my cos x terms on both sides would have cancelled, but fortunately not. Plus a half sine x. If we're aiming for tan, well, tan is sine over cos. Let's bring all the sines to the same side. If I subtract half sine x, and let's subtract root 3 cos x from both sides as well. Now I've moved that term that way. Oh, this is giving me a negative, is it not? Oh, because I haven't changed this sign, did I? When I made this little change up here, I rubbed out a minus and I put them, so I rubbed out a plus and left it as a plus. So this is going to be negative, which means these are negative. Good piece of exam technique there. You weren't expecting. So the issue I was having, if I moved that over, I would have got negative root 3 over 2 cos here. But that would mean that my tan would end up being negative, which I don't want. So I expected, I foresaw a problem. So you can go and check what you've done wrong to get to a problem like that. So we're adding root 3 over, which is going to give me 3 root 3 over 2 cos. You can do that in your calculator, root 3 over 2 plus root 3. Dividing through by cos, let's divide through by cos and multiply by 2. I've got halves that I don't like. Dividing by cos gives me 10x. And leaving behind the 3 root 3. Again, because it was a show that, I feel it's quite important that we put what we've actually done, certainly on any big final steps, so that it doesn't look like we've just cheated our answer out at the end. Okay, part B of the question. We have 2 sine 2 theta equals cos 2 theta minus 30. That doesn't look too similar to what we have before. It kind of has a 2 sine equals cos, but the things inside the brackets don't look very similar at all. However, the question said hence. Whenever the question says hence, whether you can see it or not immediately, the previous part is helpful. So something about the previous part must be exceptionally helpful for this. The previous part had that equation, yeah. So even if you can't see it straight away, and I can't see this straight away, force yourself to use the previous part. Well, the only thing we can see is maybe these things are the same, and maybe these things are the same for a particular choice of x. So let's try it. If 2 theta equals x minus 60, well, that will mean that x is 2 theta plus 60. Oh, but that works, doesn't it? Because then x minus 30 is, well, x is 2 theta plus 60. The sign's off. Oh, the sign seems to be off. But x minus 30 will be 2 theta plus 30. Which isn't what we have. Have I quoted it wrong from the other side? No. Oh, okay. So these don't seem to match up, but they should. So I'm just taking a moment to see if I've done anything foolish. Yeah, that doesn't seem to work, does it? So that might be a case where this was another typo in the paper. If that was plus 30, then it works. Negative 30 does not. Okay, well, I'm going to run, because I want my method marks, I'm going to run with that simplification. And then again, at the end, once I've got all my method marks, I can go and see if I can fix it and see if there was a slightly different thing that I should have done instead. But I'm going to run with that substitution. So that means from part A of the question, we had that tan x was 3 root 3. So therefore tan of 2 theta plus 60 is going to be 3 root 3. We had theta between 0 and 180. So if I double that and add 60, we're looking for angles of theta between 60 and 420. So we're looking for angles of 2 theta plus 60 in that range. So in my calculator, tan inverse of 3 root 3. So 2 theta plus 60 is, the first calculator answer is 79.1, and adding 180 for the symmetry of the tan curve, that is only a 360 range, so I'm only expecting 2 answers. So now let's undo the stuff. So let's subtract off the 60. So that'll be 19.1 and 199.1 for 2 theta. Divide through by 2. We only want it to 1 decimal place. Because I've kept using the answer button in my calculator, that comes out as 9.6. And if I use the other one, I will be getting an answer of 99.6. Okay. So again, at the end, go back, see if that was right or wrong. Because as it's written, I don't know if there's an X that works. We are now, though, on our final question. Use the substitution to show that. Now, we should be scared of this question. We don't often get questions of this many marks in one go. 7 marker is a lot. First thing to notice, though, this is a classic theme in this paper, something looks wrong with that question. Whenever you have an integral, you have to have a d something term. This doesn't have a d something term. Again, typo, unfortunately, in the paper. The only thing that makes sense to be there is the dx. Every integral has to have a dx, a d theta, a d something. It normally matches whichever letters inside the integral. We have x's inside, so there should be a dx there. Let's do the question. We're using the substitution x equals 2 sine theta. First thing that's incredibly helpful to do is to find your dx by d theta. Differentiate your substitution. That's going to give me 2 cos theta, which, if you like the cheeky way of writing it, is saying that dx is 2 cos theta d theta. I put that in inverted commas because that statement mathematically makes no sense. That is not a good mathematical statement, but it's a good, not quite visualization, but a good thing to think about for the question like this. So let's go back to our integral. We've got our integral between, and we have to change our limits as well, actually. If x is just root 3, then theta is sine inverse of root 3 over 2. That again is one of our super nice ratios. That's just 60. Because we're in calculus, we have to be in radians. That's root 3 over 2. And when x is 1, sine inverse of a half is pi by 6. So our limits have become pi by 3 and pi by 6. We're doing the integral of the square root of 4 minus 2 sine theta squared. 2 sine theta squared, we get a 4. You have to remember to square that 2 times by 2 cos theta d theta, replacing the dx. Now notice I did a lot in that one step. I replaced my x squared with 4 sine theta squared. I replaced the dx with the d theta, and I replaced the limits. All of those things should all happen in that one step, so that whatever d thing term you have matches the variable and matches the limit. So all those 3 things should always match in every step of your question. So now we actually need to do this integral. There's quite a lot of simplification to try and do first. First thing to notice is I've got a common factor of 4. within the square root, so I'm going to factor that out. And now probably the most classic thing in all of trig happens. We have a 1 minus sine squared. I'm going to pull my numbers out. I've got a root 4, a 2 there, and another 2. So I'm going to put a 4 out in front of my integral. 1 minus sine squared is cos squared. And I have an extra cos still sitting here. So my integral has become the integral of just cos squared. Now, unfortunately, cos squared is not an easy integral yet. You can't just integrate that to some kind of sine squared. This needs a trick. And the trick is using the double angle formulas. So you'll either recall or look into your formula booklet, and you can find out that cos 2 theta is cos squared minus sine squared. I don't want the sine squared, so this is 2 cos squared minus 1, but I want the cos squared equals version, so cos squared equals a half cos 2 theta plus 1. Now it's completely up to you whether you could quite easily just memorize each of these versions of the formula. I prefer not to memorize. I prefer to work things out from one thing. So I've memorized this one, and then I work out the others using the trig identities and rearrangement. But that's a trick that we're going to have to employ here. So we've now got the integral of, well, that half, I'm going to have that have a fight with the 4 in front. So it's just going to become a 2. And then what's left behind is cos 2 theta plus 1. Yeah, plus 1 d theta. And now we can actually integrate. This is in the form that we can do something with. The integral of cos is sine, but the 2 theta means we need to pop out a half. The integral of 1 is just theta between pi by 3 and pi by 6. Subbing them in, we've got 2 lots of a half. Sine 2 theta is sine of pi by 6, which in radians is just a half, so that's a half plus pi by 3. Subtract, when I sub in, pi by 6, so that's a half. Oh, did I do? No, I've subbed that in wrong. Okay, let's check this term here. So I'm subbing in pi by 3, so my calculator, I need to be doing sine of 2 pi by 3, because it's sine of 2 theta, which is root 3 over 2, not a half. Root 3 over 2. And then when I sub the pi by 6 in, that'll be 2 pi by 6, so that's another root 3 over 2. Plus pi by 6, and something magical happens, which we were expecting actually if we look at what the show that was. The half root 3 over 2, subtract half root 3 over 2, cancel. So I'm left with 2 lots of pi by 3 minus pi by 6. I'm doing the last steps quite slowly because I know it's a show that question. Yes, I am fine. Pi by 3 minus pi by 6 is going to give me pi by 6. And then 2 lots of that gives me the pi by 3 that the question wanted in the end. And we're complete. Okay, a nasty last question, but one that is fairly common. Unfortunately, questions like that, a horrible substitution into an unpleasant integral for lots of marks, is fairly common, so worth the time to practice. Hopefully that you found useful. If you have noticed any errors in these word solutions, please do come and have a chat. If there's anything that you want more detail on, again, come and ask. Otherwise, have a wonderful rest of your day.